Hey everyone! So what is the VSEPR model? VSEPR stands for Valence Shell Electron Pair Repulsion. So this is a theory that'll help predict the shape of a covalent compound based on its Lewis dot structure. So it'll take a 2D diagram and form it into a 3D structure. It was developed by Ronald Gillespie and Ronald Sidney Steinholm in 1957. So this theory states that because electrons repel one another, when the atoms form a molecule, the different electron pairs will be as far apart from one another as possible. So this will create the molecular geometry. And this key term means it's the arrangement of the atoms in a three-dimensional space. So how does one predict the structure? You follow these 3 steps. Let's get started. Now, the first step in determining the geometry from a VSEPR model is to first draw the Lewis dot structure of the molecule, and then count the number of electron domains around the central atom. So this includes non-binding pairs, single bonds, double bonds, triple bonds, etc. And lastly, arrange the domains of the electrons so as to maximize the distance between them. Now, there are 2 important things to keep in mind while drawing these structures. The first is that double and triple bonds are treated the same way as single bonds. But multiple bonds do have a slightly stronger repulsive strength than single bonds, so they will occupy a little more space. And secondly, the lone pairs have more repulsive strength than binding pairs, so those will occupy more space. Now, keeping those things in mind, let's get started with the first of 7 structures. So the first electron geometry is a linear shape. A common linear molecule is carbon dioxide. First, draw its Lewis dot structure, and you can see that it has 2 double bonds around the carbon atom. Each double bond is 1 electron domain, so there are 2, and there are no lone pairs. As for carbon monoxide, it has 2 atoms, and any molecule with 2 atoms will always have a linear geometry. You can see that in both cases there are no unbonded pairs to further repel against the bonded pairs. So to get as far apart from one another as possible, the 2 oxygen atoms are on opposite ends, forming 180 degrees. The next geometry is a bent structure. Water is the most common example. So following the 3 steps, draw the Lewis dot structure. And you can see that there are 2 bonded pairs and 2 unbonded pairs around the oxygen atom, making for 4 electron domains. Now, as mentioned earlier, these unbonded pairs will have more repulsive strength and will want as much room as possible to move around. Meanwhile, the bonded pairs are more restricted. So this is the actual structure. The unbonded pairs will push down the bonded pairs, hence this bent shape. The unbonded pairs will now have more room to move around. The bond angle will then become 104.5 degrees. The next geometry is trigonal-planar, and an example of this is boron trifluoride. So following the steps, you draw the Lewis structure and see that there are 3 electron domains. In reality, these domains will want to push away from each other as much as possible, creating the structure at the bottom. The bond angle becomes 120 degrees. Another electron geometry is the trigonal pyramidal structure. An example would be ammonia, or NH3. The Lewis dot structure shows that there are 4 electron domains and 1 lone pair. Now, since this lone pair has more repulsive strength than the binding pairs, it'll push down on the binding pairs just as it did with the bent shape. This creates a pyramid, or hence the pyramidal structure. The bond angle is 107.3 degrees. A fifth geometry is the tetrahedral structure. An example would be CH4 or methane. To get as far apart from one another as possible, these bonded pairs will form this shape with a bond angle of 109.5 degrees. Now, the trigonal bipyramidal and octahedral structure are shapes you'll encounter in AP chemistry. The trigonal bipyramidal has 5 surrounding atoms, while the octahedral has 6 surrounding atoms. So these atoms will arrange themselves in this way to get as far apart from one another as possible. And this is how to predict 3D structures based on the Lestat structure by following the VSEPR model. Thanks for watching.